One more way of expressing the second law of thermodynamics is in terms of order. Nature tends towards disorder because it takes a lot of energy to create order. If you remember the simplest definition of energy, it is the ability to do work. When we talk about entropy, we're talking about how much energy is not available to do work. This translates into the amount of disorder in a system. If you think about building a sandcastle, you have done work and created a very ordered system. When you come back the next day, the waves have knocked the castle down. All of those same sand particles are there, but they are no longer an ordered system. The amount of disorder in the universe has increased. What never happens, but would be totally cool, is that a castle never appears out of the waves. Remember that for a Carnot cycle, and therefore for any reversible process, that we have a relationship between the energy moving in and out of the system, and the temperature on either side of the system. We can rearrange this expression so that we are comparing the cold to the hot. The heat coming into the cold reservoir divided by the temperature of the cold reservoir is equal to the heat leaving the hot reservoir divided by the temperature of the hot reservoir. What this means then is that these are proportional to each other and therefore must be equal to some constant that will apply to any reservoir at any temperature. This constant is then defined as entropy. So for any reservoir, the heat divided by the temperature is equal to the change in entropy of that reservoir. If we take a closer look at this definition, we see that if we increase the heat energy of a system, we increase the entropy. This is actually what the second law is saying. The entropy will never decrease at the end of the process. It will increase. Now, if the engine is working at its maximum efficiency, entropy could stay the same. But we know that engines don't operate at their maximum efficiency, but it is a good idea to know that in theory, it is possible. Now, the total entropy of the system, just like you might suspect, is the entropy gained by the cold system plus the entropy lost by the hot system. And we can, of course, write it as a change in entropy is equal to the ratio of heat to temperature of the cold reservoir plus the ratio of heat to temperature in the hot reservoir. And remember, for a Carnot engine, those two ratios are equal, so we can set the whole thing equal to 0. So if you have a reversible process, the total change in entropy for a system is 0. Keep in mind that this is the total entropy change. Different parts of the system can have a change in entropy, but the overall change is 0. Since the total change is 0 and the process is reversible, there is no change to the outside environment. So reversible processes do not affect the total entropy of the universe. Calculate the total change in entropy if 4,000 joules of heat transfer occurs from a hot reservoir at 600 Kelvin to a cold reservoir at 250 Kelvin. The first thing to get out of this is that spontaneous heat transfer from the hot reservoir to the cold reservoir is irreversible. Okay, so this equation is true for reversible processes. So can we use it in this situation? The short answer is yes, because the total entropy change of the hot and cold reservoirs will be the same no matter whether the process is reversible or not. So if we pretend for a moment that the process is reversible, we can calculate the change in entropy of the hot reservoir. So let's do that. In order to determine the change in entropy of a reservoir, we simply take the heat change divided by the temperature. This is true for any reservoir, so the change in entropy for the hot reservoir in this case is negative 4,000 joules, because we are losing heat, divided by 600 Kelvin. And we end up with negative 6.67 joules per Kelvin as our change in entropy. We can set up the change in entropy of the cold reservoir in the same way. The cold reservoir gains the same amount of heat that was lost by the hot reservoir, but it is at a different temperature. So its entropy change is 16 joules per Kelvin. The total change is the change in the hot reservoir plus the change in the cold reservoir, which ends up being 9.33 joules per Kelvin. Notice this number is positive. This means that there was an increase in the total entropy of this system. So we have lost some of the original ability to do work with this energy. So we want to calculate the work of a Carnot engine operating between the temperatures of 600 Kelvin and 100 Kelvin for 4,000 joules of heat transfer to the engine. We determined an equation for maximum work possible in our initial discussion of the second law that involves the efficiency based on the temperatures of the two reservoirs and the heat energy transferred. So all we really need to do is plug in our values. Being careful to watch our order of operations, we end up with 3,333 joules of work done by this engine. So what if the heat is then transferred from the 250 Kelvin reservoir to a second reservoir at 100 Kelvin? How much work is produced? Well, we are looking for the work output again, so we can set up our problem the same way. Again, with the order of operations, we end up with 2,400 joules of work done in the second stage by this engine. So the same heat transfer results in 933 joules less work in the second process. Since the entropy change is greater in the second process, there is less work done, taking us back to the idea that entropy is the unavailability of energy to do work. So what does this all mean? If you start when the universe started at the Big Bang, you start with a very high degree of order and a lot of useful energy available. Entropy was at an all-time low. Over time, entropy has increased. The available energy has been used to do stuff. So as these processes occur, energy is being used and the amount of disorder increases. Now the energy is still around, it just gets lost into the environment. A carrot has useful energy stored in it. If you eat that carrot, the energy it contains is used by you to do something, and some of that energy is converted into heat. Either way, the energy is released in a form that cannot be used for any useful purpose. So as time goes by, the amount of useful energy decreases, entropy increases, the state of disorder increases. If you look ahead far enough, you can imagine a universe with a lot of disorder, lots of entropy, and no useful energy. A dark, boring universe where nothing happens. So find the increase in entropy of 1 kilogram of ice, originally at 0 degrees Celsius, that is melted to form water at 0 degrees Celsius. Alright, so we're melting ice. You might suspect that this is a decrease in order, so an increase in entropy of this system occurs. We want to know the change in entropy of this system. We can bring up our change in entropy equation to see that we need to know the change in heat energy and the temperature. The easy part of this is the temperature. We just need to convert it to Kelvin. Now the heat energy might be a problem, but a while back we learned how to determine the amount of heat energy change in melting ice. We were given the mass in kilograms, and we can look up the latent heat of fusion of solid water. Notice that this constant is labeled in kilojoules, so we need to be sure to write it in joules when we use our entropy equation. So from here we find that we have a pretty big increase in entropy just from melting a couple pounds of ice.